Chapter 11 is about the RMS error for regression. First, what is an error? Well, we already know that we use our regression line to predict a value of y for each value of x. And the question is, how good is that prediction? Or how far off is a single point? Because if you look at our diagram down below, our line, the line is the predicted y values. But notice that most of our points aren't actually exactly on the line. And so that's why we have to talk about our errors or our residuals. Because if you look at an actual y value and your predicted y value, there's a difference. And that difference is our error. So you can pick any y value, find the predicted y value, and the difference between the actual y value and predicted y value is your error. So to calculate your error, you're going to do your actual y value minus your predicted y value. And again, so here's our example where we have the height and the girth of cherry trees. And again, notice not all of our y values, most of our y values are not exactly on the line. And so there's always this error or residual between the actual point and our predicted y value. For example 89, I have some points I've labeled A through D, A through F actually, and we're going to go through and classify each of the errors as like positive or negative, and then maybe large, medium, or small. For point A, the error would be the distance from A to the line. Notice that A is above the line. Also, if we do our actual value of A minus the predicted value of A, which would be on the line, we're going to get a positive number. So for A, is going to be positive. And A seems very far from the line, and so I would call that a large error. For B, again, B is above the line, so it would be a positive error. And it seems pretty far from the line, so let's call it large. For C, C is below the line, so it would be a negative error. And it kind of seems like a medium error to me. It's not really far out there, but it's not super close to the line either. For D, it's also below the line, so it would be negative. And I would call it, again, medium, maybe small. For E, notice E is almost on the line. It is above the line, so it would be positive. But it's very, very close to the line, so it's definitely a small error. So we've talked about errors, now let's talk about the RMS error. The RMS error for regression tells us how far our typical or most of our average points are above or below the regression line. The RMS error measures how good a prediction is. It says how large our errors are likely to be. And the RMS error is the root mean square RMS size of the errors. So remember we talked about how to do the root mean square for our standard deviation. We're going to use kind of a similar formula here. So to find the RMS for the errors, you could take each error, square it, and then take the next error, square it, take the next error, square it, take the last error, square it, and add them all together and divide by the number of errors and take the square root. So the square is the root, the mean, that's the same thing as average, so that says add them all up and divide by how many there are, and then squares, you square each one. We're never going to do it by hand. Instead, we're going to use this nice formula. So the RMS error can be found by the square root of 1 minus r squared times the standard deviation for y. Remember, r is our correlation. So that shortcut is going to make things a lot easier for us. Let's try it out. For the men aged 18 to 24 in our Hayden sample, the relationship between their height and systolic blood pressure can be summarized as follows. So we have our height and blood pressure. It tells us the average and standard deviation for each and our correlation. Number 1, estimate the average blood pressure of men who are 75 inches tall. So we want to use the height to estimate the blood pressure. So that means height is our x and blood pressure is our y. We're going to use our regression method again. So first we figure out how many standard deviations above the average is our height. So 75 inches is, let's see, 75 minus the average of 70 divided by the standard deviation of our x, which is 3. And that gives me 1.66. So let's just write a note at our top. So our z is x minus the average divided by the standard deviation. And since we do have two variables, we could say this is average of x and standard deviation of x. So 75 inches is 1.66 standard deviations above the height average. But we can't just go 1.66 standard deviations above the blood pressure average. Instead, we have to times that by our correlation. So R times Z is negative 0.2 times 1.66, which is negative 0.33. So we need to be 0.33 standard deviations below the blood pressure average. So to find that, let's look at our blood pressure average. The blood pressure average is 124, and then we want to be 0.33 standard deviations below it. So we'll minus 0.33 times the standard deviations for blood pressure, which is 14. So this gives me 119.38 mm. And that's what we learned how to do in Chapter 10. Now let's add in our new aspect and find the RMS error of the prediction. So our RMS error, remember we're going to use our shortcut formula of 1 minus r squared times the standard deviation of y. So this is going to be the square root of 1 minus our correlation. So our correlation up here is negative 0.2. And we need to square it. And now times it by the standard deviation of y. So again, y is our blood pressure, so standard deviation of blood pressure is 14. And I just put this into my calculator and I get 13.72. One thing to note as you're putting it into your calculator, that you are squaring this negative 0.2, so that becomes a positive, and then you will subtract it. So our RMS error is 13.72. Now what do parts 1 and 2 tell us when we put them together? They tell us that, well, first of all, the RMS error tells us that the typical error is 13.72 mm. Okay, so what does that mean now if we put the two parts together? So that means for a 75-inch tall man, we predict a blood pressure of 119.38, because that's what we predicted in part 1, plus or minus 13.72, because that was our RMS error. So again, our prediction, well, that just tells us what we predict. And then the RMS error tells you how much you're likely to be off by. So we predict that it's going to be 119.38 plus or minus the RMS error. So it kind of tells you about how close you expect to be. Oh, and I guess we get it right in part 3. So your predicted blood pressure for men who are 75 inches tall should really be 119.38, give or take just means plus or minus 13.72. Now Sean is 75 inches tall. He has a blood pressure of 120 mm. So what is his residual? Now, the formula for a residual or an error is always going to be your actual y value minus your predicted y value. So that's how we find our residual or our error. So in our case, for Sean, he's 75 inches tall. He has an actual blood pressure of 120. Now we need to minus the predicted Y value. Well, notice how I said he is 75 inches tall. If you look back to part 1, it said find the average blood pressure of men who are 75 inches tall. So in part 1, we predicted that for someone his height, we would have 119.38 mm. Okay, so that's our predicted value for anyone who's 75 inches tall. So Sean would fall into that category. So in our case, we just have to do 120 minus 119.38. This gives us 0.62 millimeters. Now, it's interesting to note the predicted value, that's always the line. So he was 120, the predicted was 119. So we could say something like Sean is 0.62 millimeters above the line or above the prediction. So he's one of the people that's above the line. So again, residual or your error is just your actual Y value minus the predicted Y value. So in his case, he was 0.62 millimeters above the line. Okay, now we're going to talk about another way to interpret the RMS error. So if our scatter diagram is football shaped, now football shaped just means that a line fits it. The RMS error is kind of like a standard deviation for the regression line. And we say that because remember how we talked about for standard deviations that 68% of your points should be within one standard deviation of the line? Well, for our regression line, we can use the RMS error like that. So if you have your line, so if you look at your line and you go up or down one RMS error, about 68% of your points, so here's all your points, about 68% of your points, so not all your points, but the majority of your points should be within one RMS error. And 95% of your points should be within two RMS errors of the regression line. So if you just go up or down two RMS errors, that should include about 95% of your points. So in this example, the dashed line is our actual regression line, and then we've drawn in the lines to go one RMS error up or down. And so you can see that about 68% of your points, so the majority of your points, over half, are within that one RMS error, but not all your points. But if we go up two RMS errors, then 95% of your points, so most of your points are within those two lines. So for this example, we have our midterm and final scores for a class are summarized, and we have our averages and standard deviations and the correlation. So number one, let's estimate the final exam score for someone who got an 81 on the midterm. So again, this is just that regression thing that we keep practicing. So 81 is, let's see how many standard deviations that is from the average. So 81 minus the average of the midterm divided by the standard deviation of the midterm. So that is 1. So it's one standard deviation above the midterm average. Now we need to times that by r. So r times z. R is our 0.7. So 0.7 times z, which is 1. So we need to be 0.7 standard deviations above the final average. So what will that give us? Our final average is 60, and we want to be 0.7 standard deviations above it. So 0.7 times 10, so this should give me 67. So if they get an 81 on the midterm, we predict that they're going to get a 67 on the final. Now let's calculate our RMS error. So I'm going to calculate it, and then I'm going to read you the actual problem, what we're trying to find. So the RMS error, again, is the square root of 1 minus r squared times the standard deviation of y. So it's going to be the square root of 1 minus r. So r is 0.7, and this, we're using the midterm to predict the final. So the midterm is x, the final is y. So r is 0.7, and the standard deviation of y is 10. So it's going to be 1 minus 0.7 squared times 10. And this gives me 7.14. Okay, now what does this tell us? Remember what we set up here? That if you go up or down one standard deviation from your line, that should include 68% of the points. And so what we can say is approximately 68% of the students who got an 81 on the midterm would get between what and what on the final. So 68% of your students who get an 81 should be within plus or minus one RMS error of our predicted value. So 68% of students should be within the predicted value plus or minus one RMS error. So our predicted value is 67 plus or minus one RMS error, which is 7.14. So when we subtract 67 minus 7.14, we get 59.86. When we add 67 plus 7.14, we get 74.14. Number 3 says approximately 95% of students who got an 81 on the midterm would get between what and what on the final. So we're going to do a similar thing, but for 95% should be within the predicted plus or minus 2 RMS errors. Our predicted value for an 81 on the midterm is 67 on the final, and we want to do plus or minus 2 times the RMS error, and our RMS error is 7.14. So that gives me the numbers 52.72 to 81.28. So let's fill that in, 52.72 to 81.28. And our final question is, would you be surprised to find out that someone who got an 81 on the midterm got a 60 on the final? Well, let's look at this. Where does 60 fall inside this interval? 60 is inside this interval, right? Technically, 60 is even inside this interval. But as far as whether or not we'd be surprised, so like 95% of our students should be inside this interval. So if 60 is inside that interval, that doesn't seem very surprising to me. So from part 3, we expect 95% of students who got 81 on the midterm to get between 52.72 and 81.28 on the final. So getting 60 on the final is not surprising because, again, it's in that interval. We're expecting students to be within that interval, so as long as you're in the interval, it's not going to be very surprising. Now in part 5 here, Sally got an 81 on the midterm and 90 on the final. What is her residual, or her error? That's what the residual means. It's just another word for error. So our residual is going to be equal to our actual y value minus our predicted y value. Well, Sally's actual y value, actual final value, is this 90. Now for the predicted y value, you would have to go and predict what someone who got an 81 on the midterm should get on the final. But we already did that in part 1. In part 1, we predicted someone who got an 81, which matches Sally, should get a 67 on the final. So her predicted value from part 1 is that 67. So we'll do 90 minus 67, or 23. So Sally got 23 points above the prediction. Now, if that residual had been negative, that would have told us that she was below the line, or she got less than we predicted. But her actual y value was 90. We predicted she should only get like 67, so she actually got 23 points above our prediction. She did pretty well on that. Okay, in our next example, we're once again looking at the height and girth of cherry trees. We have our girth, we have our height. Notice one thing. When you look at this picture, height seems to be the x variable, and also we want the regression line for predicting girth from height. So we're trying to predict girth, so girth is our y. So x is height, and y is girth. And I pointed that out just because they reversed the order that they wrote the numbers in. They put the y numbers first. That can happen, so you need to pay attention. So number 1, what is the RMS error of the regression line for predicting girth from height? So we want to find our RMS error. The formula for that is the square root of 1 minus r squared times the standard deviation of y. This will be the square root of 1 minus, let's see, r is 0.52. We need to square it and times it by the standard deviation of y. So we said y is girth, so I need to use the standard deviation for girth at 3.14. So this is 2.68 inches. Number 2, 95% of your actual points, your actual observed points, should be within blank of the predicted value. Well, we know that 95% should be within the predicted plus or minus 2 RMS errors. So 2 RMS errors, so 2 times our RMS of 2.68 equals 5.36. So 95% of our actual observed points should be within 5.36 of our predicted value. And number 3, if girth is predicted from the height for all the trees, about 95% of our predictions will be within what of our true values? And that's just asking the exact same thing, although it is worded slightly differently. So in number 2, we said 95% of our actual observed points should be within 5.36 of our predicted value, which means that you can switch it around. So 95% of our predictions we made should be within, again, 5.36 of our true observed values. So that's just our 2 RMS errors. So it's just saying the same thing. So if 95% of your true observed points are within 5.36 of the predicted, then that means that 95% of the predictions are within 5.36 of the true observed values. Now let's talk about plotting our residuals. So remember, residual is just another term for the error. And our residual, or our error, tells us how far our point is above or below the line. And in some cases, regression is not appropriate, and so plotting residuals can help us determine whether or not regression is appropriate. So this is how you do a residual plot. Okay. So for each point, so here's a point right here, you say, okay, how far is this point from the line? So it's that far. This is my distance. So then I come over to my residual plot and I go to the same x value. So here x is 1, so I go over to x is 1 and I plot the residual. Notice how these two distances are exactly the same. And then I go to my next point and say, okay, it's this far from the line. So I come over to the same x value and put a point that's that distance from 0. Notice how my next point is exactly on the line. So its height is 0. This point is this far from the line, so that's the height of my point in my residual plot. So if regression is appropriate, and our textbook likes to say that the scatter plot is football shaped, but so if regression is appropriate, then the residuals are going to look like they're just randomly scattered about. Scattered about where? The horizontal line at 0. So randomly scattered about the x-axis. Also, our residuals, because some are positive and some are negative, they're going to average out to 0. And the vertical spread of the residuals seems to be fairly constant for all the x values. So we're going to talk about what all that means. So first, here's an example of some residual plots that indicate regression is appropriate. So again, these are the residual plots, the error plots, not the actual data. Notice in all of these that my points just seem to be kind of randomly scattered about. There doesn't seem to be any pattern, they're just randomly scattered about the x-axis. So these all look good. So here's some cautions. If there's a strong pattern in the residuals, it would be a mistake to fit the regression line. So here's 2 different examples where there's kind of this pattern. You can see that there is a very definite pattern, so we don't want to fit the regression line. Versus when we looked up above at our plots that were okay, notice there's no pattern in my points. And the next one is if your vertical spread isn't the same for all your x values, then we can't use regression. When we say vertical spread, we mean if you look at all the points for this x value, or about here, notice how my distance from the top to bottom is pretty big. But when I look at these values right about here, the distance from the top to bottom is a lot smaller. And over here, the distance from the top to bottom really isn't very big. And so the vertical spread changes for different x values. Okay, whereas when we look up here, notice the vertical spread. So if I was to draw it, and we're just talking fairly loosely, it's about the same for all of them. They're not really changing all that much. It doesn't have to be super exact, but there's not some distinct pattern of it changing. They're more or less the same. So let's go through some examples. So here are 3 data sets with the scatter plots of the original data and then the residual plots. And for each data set, we want to know if regression is appropriate and why or why not. So I think it helps to see the original scatter plot and then what residual plot you end up with. So the first column is our original scatter plot of the actual data. And then the second column is our residuals, which is our errors. Okay. So for my first one, notice that my points seem to be fairly linear. Okay, if I was to draw a cloud around it, it's kind of football shaped. If I look at my errors, I don't really see a strong pattern. And as far as the vertical spread, it looks fairly okay. Notice there's that one point that's a little bit up there. That's okay, we're not too worried about that. It's fairly similar throughout. And so this one looks okay. Everything looks good. There's nothing that's super wrong with it. Number 2 though, notice when you look at the residual plot that there kind of seems to be this pattern. Okay. Or if you look at the actual original data, notice you kind of see that same pattern. So there's a pattern, so we can't use regression. It is very interesting that the same pattern of your original data shows up for your errors. And number 3, even though so if I look at my original data, notice that a line is probably still the best thing that fits it. It's not a curve or anything. But over here, my residuals seem to be pretty big. My points are pretty far spread out. In the middle, they're pretty close to the line, and then over here, my points are spread out again. So a football shape isn't appropriate here. I can't just draw a football. That doesn't work. It doesn't seem to represent my data. Okay, and when you look at the residuals, there's a very big vertical spread here, a tiny vertical spread, and a big vertical spread. So the vertical spread changes. And anytime your vertical spread is changing like that, you can't use regression. So here are the original scatter plot and residual plots for our height and weight data from the textbook. So we're asking kind of what do we notice here? First, I'd like to point out that this first one is our original data. Or it's the scatter plot. The second one is our residual plot. So there's a few things we want to look for. So first, let's check to see if there's a pattern. I don't really see a pattern. Linear seems fairly good. Okay, so we're good on that. Now vertical spread. If we look at this, and you can look at the scatter plot or the residual, they'll show you about the same thing. If I was to look at this, it looks like my vertical spread is fairly constant. I have a little issue right here maybe, but I'm not going to say it's a really big issue. It seems fairly constant. And then, so far we're not doing too bad. Maybe this might make me worry a little bit. The textbook must not have been too concerned. They've had us do it use this data set a few times. There are other things you can do to your data that you learn in other classes that can make this look even better before you do it. But there are two problems. Notice this outlier here and here. They will show up in the scatter plot. They will also show up in the residual plot. So there are two outliers. Now, depending on how bad the outliers are, all of this is very subjective. Some people say this one was probably okay. Some people say it wouldn't. I can tell you that the person that writes our exam would say that this is not okay. So as you're studying, these outliers would say, probably not okay, so I probably wouldn't use regression. Now, maybe the book just wanted to use it for an example. Maybe also because there's hundreds of other examples, those two aren't affecting us as much, so it might be more on the okay side because of that. But I do know the person that writes the exam would, if you see outliers like this, she would say no. And finally, just a little bit of vocabulary for us. is homoscedastic versus heteroscedastic. Now, those words do seem horrible, but notice or focus on the root. Homo always means the same. Hetero means different. If we talk about the root of the words. So if our vertical spread is the same for all our x values, so if the vertical spread seems about the same, we call the data homoscedastic. If our vertical spread isn't the same, we call it heteroscedastic. So you will see that term occasionally. Homoscedastic means the vertical spread is the same. Heteroscedastic means the vertical spread changes. Now we should only use our RMS error and linear regression for homoscedastic scatter diagrams, because if your residuals are changing from like kind of a small group to a big group, your RMS error is just going to go completely out the window. And just to note that if you don't know what the scatter diagram looks like, it's going to be dangerous to do your linear regression. And so if you haven't seen the diagram, we're just assuming that it's football shaped so we can do our regression for this class. If this assumption is incorrect, your data might not be accurate.